So my name is Amanda Gallinat. I'm a postdoctoral researcher at Utah State University working with Will Pierce, and I am very excited to talk to you today about integrating evolutionary history into our forecasts of species assembly. This is a framework that Will Pierce and I are working on together right now, and so I'm excited to hear your feedback and learn from you guys over the next few days and incorporate that learning back into this framework. When I say species assembly, what I mean is where species occur and where they co-occur together. We want to know about that for a few reasons. One is we want to understand how species distributions, like this common loon, are changing. We want to know where invasive species, like this kudzu or brown marmorated stink bug, will establish and persist. And we want to know where associated species, like those connected by trophic dynamics or pests and pathogens and their hosts, will co-occur and potentially interact in the future. And we can think of three broad processes as generally driving species assembly across space. Regional environmental limitations are the environmental sensitivities that constrain where species can occur on a regional scale. Assemblage structure refers to the local species of the same guild that might constrain where a species is based on, for instance, interactions like competition and facilitation. And the biotic environment refers to those cross-guild associations that may constrain where a species can be based on whether its associated species are present. In order to model all three of those processes together, we need cross-guild local assemblage data that connect at a regional scale. And that is a really tall order. So there are two organizations, so NEON and TERN, for instance, are collecting this kind of data, and they're doing it at an annual or finer temporal scale that should allow us to make some predictions, iterative predictions, you might say forecasts, about where species will assemble. So what can data like these and phylogenies tell us about where species will occur? First, phylogeny can tell us whether closely related species share environmental sensitivities. So for instance, at this regional scale, you can see that close relatives pink and blue share some of their sensitivities, whereas close relatives orange and yellow do not. We can take a trait like environmental sensitivity or others, and we can map that onto a phylogeny. Using that phylogenetic structure of traits, we can impute sensitivities for species that we don't have data for. So we can get at non-target species, and that can really improve our parameters for those species. Phylogeny can also help us predict the structure of local assemblages. So if at the regional scale we see those three species, yellow, blue, and pink, overlapping, at the local assemblage scale, we might actually see that those close relatives, pink and blue, do not overlap at all. They rarely co-occur. And so if we can identify those phylogenetic structures of community assemblage, are closely related species found together, or are distantly related species found together, then we can start to predict, for instance, whether an invasive species would do well in a local assemblage based on its phylogenetic distance from that community. And finally, phylogeny can help us understand and predict species co-occurrences. So if we have not one guild, but two at that local assemblage level, we can map those co-occurrences onto phylogenies, and we can understand the phylogenetic structure for those co-occurrences. And that can help us understand whether those co-occurrences and associations are due to, say, coevolution, shared environmental responses, or chance. This can be really helpful for predicting rare events like zoonotic outbreak or host shifts, which we know have phylogenetic structure. So last, I want to say that tools for ecophylogenetic analysis are really improving, from this phylogeny that Darwin drew in The Origin of Species to phylogenies, present phylogenies. You can build your own phylogeny using GenBank data, using any number of tools, including these listed here, or prune existing high-resolution phylogenies to meet your species list. And Will and I are also in the process of developing this framework, applying it to NEON data. And so in that process, are working on improving the statistical methods like phylogenetic generalized linear mixed models for big data sets like NEON. So I want to say thank you to my funders, my collaborator and supervisor, Will Pierce, and to EFI and to the Burns Center for bringing me here. Thank you.